Hello everyone, let's get started. In the last video, we discussed uh, minor of the matrix and cofactor of matrix, and also we discussed how to calculate the inverse using the cofactor matrix. Then we also discussed the important properties of this differentiation. We derived this one, right? Okay. So in this video, I think our number 7, right? Okay. Number 7 in this matrix algebra discussion, it is one of the important stuffs in engineering problem, eigenvalues problem. Okay, so let's take let's define what is eigenvalue problem first, right? So we already discussed when you multiply a matrix into a vector, you will get a vector, right? So this one actually a vector, right? So let's say this is vector y. Okay, this definitely a vector. We already discussed this one, right? Okay. So now we will get one special situations when you multiply matrix into a vector, you will get the vector that is magnification or shrink of the current vector. So that means this vector into one uh, constant, right? Okay, this constant, this one is called eigenvalue. Then the corresponding vector, in this case, you are multiplying one matrix and one vector. If you get that vector with the constant, then this vector called eigenvector. This vector called as a eigenvector, right? Okay, so these are, I think, the one word, right? Eigenvector, eigenvalue is one word, right? So not a two word. Okay, right. Let's say, how can we solve this problem? If you take it this side, right? Let's say A matrix vector X minus lambda. You know, we can introduce identity matrix here, right? When you multiply identity matrix into vector, you will get the same vector, right? It is 0. Now, if you take X vector out, that means don't take it front, right? That means this is the post multiplication, therefore you can take it back side, right? That means A minus lambda I identity matrix, it is this equal 0. So in this equation, if you want to solve this equation, there are two solutions. One is if this matrix, right? So that means A minus lambda I, right? If this matrix, if it is singular, you know what is the meaning of singular? Singular means determinant of A minus lambda I is 0, right? Okay, if it is singular, then this x can be anything, right? No matter whatever x, this equation will satisfy. Another one, if this matrix is non-singular, so that means determinant of this one is not equal 0. Therefore, definitely this vector x must be 0, right? Then only this equation will be satisfied, right? In this case, x vector is 0, but we are not interested in the 0 vector, right? It's not interested. This is called trivial solution. So not interested, right? So we interest only the first part, right? So that means determinant of this one is 0, right? Okay, so let me move it to next page. Let's say if your matrix n A is n by n matrix, right? Because determinant you can talk about only the square matrix, right? You can define for non-square matrix also, but if equation form you can define only for square matrix, right? So what is this matrix actually? A11, A12. So like that you will get A1n, right? So this is A21, A22, like this A2n, right? Similarly, this one AN1, AN2, okay, this is ANN, right? Okay, so this is your matrix, right? So then the determinant of A minus lambda I, right? Identity matrix, that is only the diagonal matrix, identity n by n matrix, right? So that means this one here, 1, 1, so like that 1, right? So another everything is 0. Okay, right? This also 0. Okay, so this is actually n by n matrix, right? So that means here lambda is there. So what is this one? You will get determinant, that means determinant of, okay, determinant of A11 minus lambda A12. Only the diagonal term you have to reduce, uh, subtract the lambda, right? A1n. So this is A22. So this will be A2, A21, right? This is A21. A21, A22 minus lambda. So this is A2n, right? Similarly, this is AN1, AN2. Okay. Okay, here you will get ANN minus lambda, right? Okay. So this is actually equal to 0. That is the solution, right? Non-trivial solution, right? Okay. So that means here you will get the equation in lambda, right? This is N1. Equation of lambda. That means nth order polynomial you will get, right? Nth order polynomial equation, right? So this equation called characteristic equation, right? How many solution you will have for the lambda? N solution, right? Okay. So this has n solutions. So that means n number of eigenvalues we will get. For each eigenvalues, we will get corresponding eigenvector, right? So that means n eigenvector you will get here, right? Okay, it's fine, right? This is I am not going to discuss much because you have done a lot of questions, in your matrix algebra. So let me take one question, right? One exercise example. Uh, let's take a matrix A. It is 2 minus 1 minus 1 1, right? Okay. Right. Yeah. So we need we need to calculate determinant of A minus lambda I, right? Equals 0, right? So here I must be 2 by 2 matrix now, right? That means 2 minus lambda minus 1 minus 1 1 minus lambda, right? Equals 0, right? So therefore the equation is 2 minus lambda into 1 minus lambda into minus 1 equals 0, right? So that means lambda squared minus 3 lambda plus 1 equals 0, right? Uh, yeah, you can calculate lambda here because this is not simply you cannot factorize. So in this case, let me write the answer I get, right? 3 plus or minus square root 5 over 2, right? It is approximately 0.382, comma, this is one solution, another solution 2.618, right? Okay, so now let's calculate the eigenvector, right? That means it is eigenvector problem that we discuss, right? A vector minus lambda I into vector x equal 0, right? Okay. Let's take the lambda 1, right? Lambda 1 equals 0.382, right? Okay, we will calculate the corresponding vector 1, right? Okay, so in this case, matrix A, let me bring matrix A is this one, right? Okay, let me bring the A here. Right. So that means A minus lambda 1, this one, right? If you substitute that matrix A now, 2 minus this one, 1.618, right? Then minus 1 will be there. This will be minus 1. And this is 1 minus 0.682, 0.618, right? Yeah. Into vector x, right? x1. Okay. X1. Okay, I'll take it x1 like this, x1, x2, right? Equal 0, right? That means 0, 0 is 0 vector, right? Okay. Yeah, if you multiply this one, 1.6 618 x1 minus x2, here minus x1 plus 0.618 x2. This equal 0, 0, right? Okay, right. So this equation we can calculate simply. Okay, from the second one you can write x1 equal 0.618 x2, right? Okay, right. So therefore your vector eigenvector 1, right? Oh, that means for lambda 1, right? Lambda 1 0.382, right? Okay. For this vector eigenvector 1, x1 x2, right? X1 you can write in terms of x2, right? 0.618 x2. X2 you can keep it same, right? So this is kind of a vector, right? You need this is direction. You need only one direction. That means x2 you can choose any value. Then if you take it if x2 equal 1, therefore this eigenvector is 0.6181, right? So normally we will get the normalized vector. Okay, no issue. Then we will keep it as it is, right? So for example, if we want to calculate the eigenvector for the second case, the value is what is the value? It's 2.618, right? In this case, the same way you can calculate, then I will write the answer that you can check it by yourself. So I get 1 minus 0.618, right? Okay, so this is the answer for eigenvectors, right? Okay, right. Uh, okay, so now I'm going to discuss one more important things, right, regarding this eigenvector. Uh, in in eigenvector, there's another important stuffs regarding the matrix, right? It's called, I don't know whether everybody studied these things in your linear algebra. If you studied some advanced linear algebra, the following things you will you might have discussed there, right? That is called spectral decomposition. Decomposition theorem, right? I'm not going to derive this theorem because that is out of the scope of our discussion, because we are discussing the continuum mechanics, right? You can derive, right? Using linear algebra, there are theory you studied, you can derive, right? It's not a difficult. Um, so let's take any matrix A. Let me explain the theorem, right? N by n matrix. Then this matrix, it can be decomposed into this way, right? L, okay. Uh, L is a matrix. I will tell you what is L matrix. L, and uh, so I will use this notation because same notation they use. Okay, this also a matrix L inverse. Okay, so this is any matrix A can be decomposed into this way, right? What is actually this matrix, right? This is called eigenvalue matrix. That means you will list out all the eigenvalues. For example, let's say all the eigenvalues, right? Here, along the diagonal, the remaining part is 0, right? All off diagonal part is 0, right? Okay. This is your matrix. This one, diagonal matrix contains eigenvalues. Then what is matrix L is a eigenvector, right? That means it is a matrix of eigenvector, right? Eigenvector 1, eigenvector 2, okay. This is okay. So this is actually n by n. That means 3 by n matrix, right? So this is n by n matrix. This is 3 by n matrix. How 3 by n? Because this is a vector, right? The first one you have three components, right? X1, x2, x3, right? Similarly, second one, x21, sorry, x12, right? Sorry. The second vector, x1 component, right? x22, x32, right? Similarly, right? Like this, finally, n1, xn2, 2, sorry, it will be xn2 xn3, right? So this is actually 3 by n matrix, right? Okay, so this is any matrix you can decompose into this way. How this one is useful, right? Again, one more thing, right? If it is A is symmetric matrix, right? Symmetric matrix, in this case, definitely so again, this will be not 3 by n because we are considering n by n, right? This is n by n matrix, right? Okay, so this is continue until n, right? Because n dimension, I'm not considering the 3 dimension, n dimension, right? Okay, so if it is symmetric matrix, A is a symmetric matrix, then you will get this, the L inverse, it is an orthogonal matrix, right? So that means L transpose you will get. So where in case of the symmetric matrix only. In that case, this is you can write L eigenvalue matrix L transpose. Okay. So this is where when A is a symmetric. Symmetric. If A is general, so in that case, your matrix A, you can write L A inverse. So this is the only different, right? Okay. So let me take the general case. When it is helpful for us. For example, if you want to calculate A squared, right? So A, you can write it like this. This is matrix A into matrix A, right? Okay. Matrix A into matrix A. Right? So that means L A L inverse. Okay. The second one L eigen value matrix into inverse. Right? So when you multiply this one, you will get, you see L inverse into L, right? L inverse into L, right? So this is identity matrix, right? So identity matrix into matrix, the matrix, right? So that means L lambda into lambda. Lambda is a diagonal matrix, right? Lambda into lambda, only you will get lambda squared along the diagonal. Other everything is zero, right? This is simply lambda squared, right? Then L inverse. Okay. So lambda squared is very simple, right? It is not a difficult because you will get lambda 1 squared, lambda 2 squared, like that, lambda n squared. So now everything is zero, right? Okay. Similarly, if you can write this one for nth power of a matrix, simple, right? This is the important properties of this spectral decomposition of a matrix. Okay. Otherwise, it is very difficult, right? Matrix multiplication. A3 mean A into A into A. That means first you have to multiply first 2, then multiply again. Then it's very difficult. But through this spectral decomposition theorem, we can easily calculate. But if A is symmetric, even it is very simple, right? L you can find L transpose. It's no need to even find the L inverse, right? In case of uh, A is symmetric, right? Okay. So I think this is the right time to stop this video. So let me stop at this point, and I will meet some other video, right? In next video, I will start the another important part in the continuum mechanism. I'm going to start divergence, curls, and gradient of a vector, right? Okay. Of a vector, a scalar function. Since those things we are going to discuss, that is very important things, right? So after that, I think that's all our maths preliminary. Then we can move to our uh, uh, lectures directly, right? Continuum mechanics lectures. We can start, right? Okay, so let me stop at this point. Then please like, share among your circles. Also subscribe if you have not subscribed already. Thank you very much.